Hello, everyone. Welcome to another wonderful day of chemistry as we continue our conversation about titrations. So today we're going to be moving on to weak acid, strong base titrations. And it turns out these are probably one of the most common types of titrations you'll end up finding. One of the reasons why is it turns out that a lot of interesting compounds are weak acids, and it's very easy to use a strong base as your titrant. The most common sort of strong base you're going to be using is going to be sodium hydroxide. It's very easy to work with, and as long as you've standardized it against something like phenolphthalein, it's very easy to use. So the key point of most titrations is going to be trying to relate the moles of the strong base versus the moles of the weak acid you're adding. But it turns out we can find a lot of extra information about the system along the way. So we can go ahead and construct a titration curve for this sort of titration, where now we're adding our sodium hydroxide to a weak base instead of a weak acid. And you'll notice that the curve looks fairly similar to the weak acid with a couple notable differences. But in principle, we can do a lot of we can treat it very similar to a strong acid base titration, as we can break it into four key parts. What is my pH initially? What's the pH before the equivalence point? Trying to identify the equivalence point and its pH, which you may notice is shifted from the 7 for a strong acid base system. And then again, treating the system post equivalence point. So we're going to have to start with the same way with a set of ice tables, and then we're going to have slightly different equations at each of these 4 points than we did previously. So let's go ahead and jump into it and look at that initial point. So let's go ahead and for our titration system, let's go ahead and look at adding our strong base titrants is 1.1 molar sodium hydroxide, just like last time. But now instead of 25 mils of HCl, we're using acetic acid, again, still with that 0.1 molar acetic acid. That way the molarity of the two systems lines up and it makes our calculations a lot easier. It is worth noting acetic acid does have a pKa of 4.75, which is going to come into play. So the first part of any titration is trying to identify what the pH of the system is before I've added any of my sodium hydroxide. Well, at this point, our system is composed of just that 0.1 molar acetic acid. So it turns out we've got a weak acid system. So we use the same techniques we had before. So we can go ahead and start with our 0.1 molar acetic acid, decomposing into acetate and free protons. So we're consuming the acetic acid and producing the acetate and protons. So then our equilibrium concentrations can be given simply by these differences. Now, when we go ahead and plug this into our equilibrium constant, we can go ahead and turn that pKa into a Ka. Again, with the equilibrium constant being 10 to the negative pKa, so about 2 times 10 to the negative fifth, and that should be equaling products over reactants. And as usual, we're going to start with the approximation that we can drop the x, assume that our x is pretty small. We'll double check that later in a sec. So we can go ahead and rearrange the equation to solve for x, which should be given as the square root of our initial concentration times the Ka. When we plug in the values, we find out that our x, which is the same as our proton concentration, should be about 0.0013 molar protons, or 1.3 micromolar. And you will notice that that really won't affect the sig figs on our acetic acid, as it's about 1% of our initial starting concentration. So meaning that it won't play a major role in our ice table. So our approximation was pretty safe. Now that we have the proton concentration, however, we can go ahead and plug that into our pH equation, use our proton concentration to plug in here, and it turns out we're going to have a pH about 2.87. So it is worth noting that for a strong acid system like HCl, the pH was about 1.87, so we're much higher concentration. So let's go ahead, start as a pH of 1, so again, much higher concentration. Now let's go ahead and see what happens when we start adding our sodium hydroxide. So once we start adding the sodium hydroxide, we'll look at that same 10 milliliters of the 0.1 molar sodium hydroxide we did for our strong acid system. Now, one of the big notable things is we're going to do the same thing we did last time, use an ice table to calculate the exact amounts of our weak base formed. And again, for that, we need to figure out the moles of our sodium hydroxide and the moles of our acetic acid. So the moles of sodium hydroxide can again be given by the volume of sodium hydroxide used times its molarity, gives us a value of 1 millimoles of sodium hydroxide. And we have about 2.5 millimoles of our acetic acid, which again, here I'm denoting as HA because it takes less time and less space to write out. So we can then plug that into our full ice table, and remembering that this reaction will go to completion. So we're going to react our hydroxide and our acetic acid till one of them is completely consumed. And that's a key feature of these titrations, that you will always either consume your weak acid or your strong base. In this case, we have less of our hydroxide, so that will be completely consumed, leaving 0 moles of hydroxide. And this gives us an X of 1 millimole. So we have 1.5 millimoles of acetic acid remaining. However, last time we ended up producing a salt. This time we end up producing 1 millimole of a weak conjugate base, namely acetate. So in this case, we've got a conjugate weak acid base pair. That means we've got a buffer. So one of the notable things is you can use a titration to generate a buffer along the way, which means we need the concentrations of both the acetic acid and the acetate. So from here, we can go ahead and make use of the volume, the total volume of the system. So we started with 25 mils and we added 10 mils. So we had 35 mils total. And here I'm using the shortcut method of millimoles over milliliters, still gives you units of molarity. So the molarity of our weak acid will be about 0.043 molar. And the molarity of the conjugate base will be about 0.03, so about 30 millimolar. So we can then use these two values to plug into our Henderson-Hasselbalch equation, with again remembering that it's going to be pKa plus the log of the base, so in this case acetate, over the acid, in this case acetic acid. So our pKa here is 4.75. We're going to be slightly richer in acid, so our pH should be slightly lower than the pKa. So at this point, after having added 10 milliliters of sodium hydroxide, the pH is going to be about 4.6. So it is worth noting that our pH is going to be slightly less than the pKa of the acid, as the acid is the principal component. If we have added slightly more than half the number of moles of sodium hydroxide, we'd expect it to be slightly more basic than the pKa. So this whole region of adding less than 1 full equivalent of base is essentially going to generate a buffer. There's a very notable point in this buffer calculation where we've added half the amount of moles of our strong base as we have weak acid. This is referred to as the halfway point because I've added half the number of moles. However, this ends up generating a very cool feature. We can look at this by seeing what happens if I add 12.5 moles of sodium hydroxide, 12.5 milliliters of sodium hydroxide to that 25 milliliters of acetic acid. So when we do this, we can find that we have 2.5 millimoles of acetic acid, just like before. But now we have 1.25 moles of hydroxide. And as I consume the hydroxide and produce acetate, it turns out that we will have consumed exactly half the number of moles of acetic acid and generated an equivalent amount of acetate. Now, this is a very cool feature, as I have equal number of moles of my acid as my conjugate base. And if you remember your Henderson-Hasselbalch, this ends up generating a very cool feature, because if the number of moles are equal, it means that so are the concentrations. And when the concentrations of acid and base are equal, that is the exact moment when the pH equals the pKa. So this means that without having to do any real calculations, simply by knowing I added half an equivalent, I know that the pH is going to be equal to 4.75, simply because that's my pKa. So as I add more sodium hydroxide, that pH is going to continue to increase as my buffer will now be richer in base than acid. Now this continues till we reach another really interesting point, which is again our equivalence point, just like we had for strong acid. So at this point, I'm going to need to add 25 milliliters of my sodium hydroxide to 25 milliliters of my acetic acid. Again, I'll note that this will generate equal number of moles as the molarity of both species is equal. So we can use our ice table to figure out exactly how many moles of product I produced and how many moles of each reactant remain. So at the equivalence point, just like for a strong acid system, I will completely react both the acetic acid and the sodium hydroxide. So this leaves me 0 moles of each of my products or of my reactants and generates exclusively 2.5 millimoles of acetate as I've converted all of the acetic acid to form acetate. So at this point, the only acid-base component I have left in the system is going to be that 2.5 millimoles of a weak base. No weak acid, no strong base, just that simple weak base. So if I'm going to try and determine the pH of the solution, I've got to determine the concentrate of my acetate and its pKb, so I can then use a separate ice table. Happy, happy, joy, joy. So at this point, I know that my total volume should be 50 milliliters, as I've added 25 milliliters of sodium hydroxide to my 25 milliliters of acetic acid. So at this point, I have a 0.05 molar solution of acetate, and my pKb can be obtained by just taking the 14 minus the pKa. So I've got a pKb of about 9.25. Then using these two values, I can generate an entirely new ice table, looking at exactly how much hydroxide is going to be produced from the decomposition of my acetate in what essentially is water. So a good way to think about this is my hydroxide consumed almost all of the acetic acid, but a little bit remains. So we go past the point, assuming that we just made acetate, and figure out how much back reaction we have. So at this point, I know I'm consuming my acetate, generating some hydroxide, and we're going to assume that the amount of acetate consumed is essentially negligible. And then using that to figure out the concentration of the hydroxide. So we can then plug this into our equilibrium constant, which can be given as 10 to the negative pKa, which is about 5.6 times 10 to the negative 10. And again, that will equal products over reactants, again, assuming X is small. And by solving for X, which will be the same as both the hydroxide and the acetic acid concentration, we find that, yes, that value is actually quite small. In fact, it's on the order of 5 times 10 to the negative 6. So really will have very negligible impact on that 0.05 molar acetate concentration. So from here, since we have the hydroxide concentration, we can then use this to calculate the pOH by taking the negative log of that hydroxide concentration, which produces a value of about 5.3. However, turns out what we're actually interested in is the pH. So we'll do 14 minus that pOH, and this gives us a pH of 8.7. So this should hopefully make sense, as we had the solution dominated by a weak base. So we should have a slightly basic solution. And indeed, that's what we see here. So it is worth noting that when we had a strong acid-base system, the system should have been perfectly neutral as there was only water present. However, here the pH will be higher as it's now dominated by that weak base. So this brings us to the last region of our weak acid titrations. What will end up happening if I add excess hydroxide? So I go past the equivalence point. So in this case, we're going to do just what we did for the strong acid titration and use 30 mils of sodium hydroxide. So this puts us 5 milliliters past that equivalence point. So we can then Just like before, construct a ice table, noting that we start with 2.5 millimoles of acid and 3 millimoles of hydroxide. Using this, we'll then send the reaction forward till one of these species completely reacts. At this point, acetic acid is now the limiting reagent. And using that, we can find that our X value is 2.5. So we produce that same 2.5 millimoles of acetate. And this leaves behind about half a millimole of hydroxide, which may not seem like a lot, but note that the decomposition of acetate generated very little hydroxide. So most of the hydroxide in solution is going to come from this little remnant of our strong base. And as a result, what we're going to find is that while there is a weak base present, whenever there's a strong acid or base present, it will always dominate the pH of the solution. So we can simply get the pH of the solution by finding the concentration of our strong base. So we know how many millimoles have been unreacted, and we know the total volume of the system by taking the combination of our original 25 milliliters with the 30 milliliters added. So using this, we find the concentration is about 9 times 10 to the negative third molar, or about 9 millimolar hydroxide. Using this, we can then find the pOH by doing negative log of this concentration. And it turns out the pOH is about 2. We can then calculate this as the pH. And if these numbers seem familiar, it's because this is the exact same values we had for our strong acid titration. And it makes sense because in both cases, we had half a millimole of hydroxide remaining in the system. And it doesn't matter what else is present in the system because this dominates the pH. So whether you're in a weak acid or a strong acid system, once you get past the equivalence point, it all looks similar. So we had a lot of different moving parts to this titration. So let's go ahead and recap. So whenever you're doing any sort of weak acid titration, the first step is always to use an ice table to see where on the titration curve you are. Have you not added any base yet and you only have a weak acid? At which point, congratulations, it's going to be fairly easy to solve. You use your weak acid calculations and there you go. However, if you've added some strong base, you'll have converted some of your weak acid to a weak base. And whenever you have a combination of a weak acid and base, you're looking at your buffer region. So then you'll use Henderson-Hasselbalch to solve the equations here. Once you've added one full equivalent, for that very brief moment in time, all you have present in solution is a weak base. Though note that in terms of the volume space of this calculation, this is a very small region. And in this region, the pH almost always changes very quickly. Once you've added just a little bit of excess of your sodium hydroxide, then that will quickly dominate the pH of the system, and you'll slowly move on to whatever the pH of that strong base solution is, as you're now more looking at a simple dilution calculation. Now, this brings to the last important point when you're doing these calculations. Make sure to include dilution, because as you go through this whole titration, your total volume is increasing. That won't be a major issue at the initial conditions, as you've added no volume, and the buffer cares much more about the moles of acid and base than it does about the volume. However, once you get to this end point, the weak base does depend on the amount of volume present, as well as when the strong base is prevalent, as the pH is predominantly controlled by the amount of volume added. So next time, we're going to go ahead and flip the system a little bit more, as we're going to add a strong acid to a weak base. Until then, take care.